I am Professor Charlie Collins, and this is your daily dose of statistics. Today we're going to continue down talking about inferential statistics, and particularly understanding inference and more specifically, hypothesis testing. So we are on lecture number 3 of 6 of the hypothesis testing pieces. And today we will be talking about the paired sample or related sample test, related sample test of significance. Now this is a unique test of significance. It's slightly different than the other ones. And the use of the paired sample test of significance, it's also called a related sample t-test. The use of this test is to typically look at change over time. So you have the same group of people being measured twice. And what you're doing is you're comparing the means of time 1 versus time 2. Typically we use this test for pre-post types of studies, right? Where you're looking at something, you're looking at a baseline measure, you're doing some sort of intervention or a program or something like that in between, and then you're measuring afterwards. And so let's take a fairly typical example and think about a weight loss program. So this will be a running example throughout the lecture here. And let's say we're interested in the research question, do participants in a 3-month weight loss program lose a significant amount of weight at the conclusion of the program, so at the end of 3 months? So what we're doing is we're taking the before and we're taking the after, and we're comparing those two. And so we have two measures here. We have people's individual weights pre-program, people's individual weights post-program. So these are actually two different variables. They're a pre-program variable and a post-program variable. And what we're doing is we're comparing the means of those two variables, or we're comparing the scores on those two variables. So it's interesting, so while the other t-tests actually directly compare the means of the two scores, the paired sample t-test is slightly different, as we will not be comparing means per se, but we'll actually be comparing difference scores. And we'll talk about those when we start calculating the test. And so we'll go through our 5-step model of calculating our t-statistic. Steps 1, 2, and 3 are very much like the other tests you've seen, and we'll go over those anyway. So let's make assumptions. Let's do step 1 and talk about making assumptions and meeting those test requirements. And so, of course, we have to ensure that our sample is random, right? We need a random sample. The sampling distribution is normal. The normal distribution is there. And we have to make sure that the level of measurement is interval or ratio, right? Or interval ratio measurement. So that outcome variable needs to be a continuous variable. So again, thinking about weight, for example, right? Weight is an interval ratio type of variable. Step 2, we state the null and research hypotheses. Again, this is very similar to what you've seen before. In this one, though, take a note on the notation. The notation is slightly different. So again, let's revisit our research question. Do participants in a 3-month weight loss program lose a significant amount of weight at the conclusion of the program? And so our null hypothesis here is the opposite of what we would expect, right? So what this is stating is that, so the notation here, and remember, H sub 0 is our notation for the null hypothesis. It's our symbol for the null hypothesis. And so what this is saying is that people in, or weights at the pre-measurement are equal to or less than the post-measurement, right? We want the post-measurement to actually be less than the pre-measurement. So the null hypothesis is the opposite of that. The research hypothesis, on the other hand, states that participants lost weight at the conclusion of the program. So we should see here that post-weights should be less than pre-weights, right? And that's what our notation shows here in our hypothesis. And again, remember H sub 1 is our research hypothesis symbol. Now let's go to the critical region and 1 and 2 tailed test. And so last lecture we briefly discussed degrees of freedom. Our sample size in this case is really small, it's 15. And so what we're going to do is we're actually going to use degrees of freedom and to calculate our critical region, or to find our critical region in our t-test table. And so again, let's visit our research question. Do participants in a 3-month weight loss program lose a significant amount of weight at the conclusion of the program? Right. So this lose here, highlighted in red, this indicates that we're interested in a direction. Right. So it's not just is their weight different, but we're actually looking at the direction of their weight loss. Right. We're specifically stating loss. So in that case, we're looking for a one-tailed test and not a two-tailed test. If we were asking the question if they would just be different, then we would be doing a two-tailed test. But in this case, because we have direction, it's a one-tailed test. And so as you see here, we're looking at the left side of the distribution on the negative side of the distribution because we're looking at weight loss, not weight gain, right? So now let's take a second to talk about degrees of freedom. And this t-test is like the previous t-test, the single sample t-test. So again, remember our t-distribution varies by sample size, where our t-distribution when we have low sample sizes like this is going to be a little more flat compared to our standard normal z distribution. And the way we calculate degrees of freedom, and so we're going to use this idea of degrees of freedom to calculate our critical region. And so we have this idea of degrees of freedom that helps us identify this critical region. And so degrees of freedom is calculated by n minus 1. And in this case, for the paired sample, it's the number of paired cases, not the total number of measures. Right? So we have 15 cases measured twice. It's not 30, but it's 15 because we only have 15 cases. So in this case, we have 15 minus 1, so our degrees of freedom is 14. And so what we can do is we can come over to our t-test table here, our t-table, and first we need to identify what our alpha level is. And so remember, we typically use the alpha level of 0.05. That gives us 95% confidence in our test. And because we're using the one-tailed test, we want to use the 0.05 in the top row here. And then we use our degrees of freedom. So what we do is we identify our degrees of freedom, and what we did is we calculated 14, remember? And so we go down and we find our 14, and we put our 0.05 column with our 14 row, and we'll find our critical region. So right here, our critical region is 1.761, right? So this critical region, what we're doing is we're identifying the place at which our test needs to be above, right? Or needs to be beyond. So if we come back here and look at our table, what we're looking at is a negative 1.761. That is our critical region. So what we're trying to do is identify, when we calculate our test statistic, if our test statistic will be beyond this region, right, in the shaded area. So in this case, because it's negative, anything less than negative 1.761 would be considered beyond this critical region. Now we need to compute our test statistic. And so again, we have our means, our standard deviations, and again, we're looking at weight loss between the two groups. Our test statistic here is slightly different than what you've seen previously in say, a single sample t-test, for example, or a single sample z-test. And that's because we're not necessarily calculating the mean differences between the two variables, or between pre versus post program, but we're calculating different scores, and we'll see what that means in a second here. So here's our basic example of our paired sample t-test equation. And so what you see here, and this is to calculate our observed t-value. And so what you see here is at the top we have the sum of the difference scores divided by the sample size, which is all divided by the square root of the sum of the squared difference scores minus the sum of the difference scores squared divided by n, and then that is over n times n minus 1, and then we take the square root of that. So this seems like a fairly complicated equation. However, if you do it, it's not extremely complicated if you do it step by step, right? So solve n times n minus 1 first, for example, then solve the sum of the squared difference scores squared, so on and so forth, and then each little component of that, it might take several steps, but you can get there fairly easily without a lot of complication if you just solve each little piece by itself. So you're probably wondering what the sum of the difference scores is and what the sum of the squared difference scores is. So we have a little video here that will talk about that in just a second here. And so what this video does is it is showing how to calculate the sum of the difference scores, also sum of the squared difference scores. We are going to run through calculating sum of the difference scores as well as sum of the squared difference scores. Now these two are really important to distinguish, so this calculation is for the paired sample t-test. And these two calculations are really important to distinguish because the calculation or the equation for the paired samples t-test asks for the sum of the difference scores squared, and it also asks for the sum of the squared difference scores. Now these two are very distinct, and they come up with completely different calculations or completely different results. So it's important to know the difference. It's absolutely essential to know the difference. So we will go through the calculation real quick of both of these, and we will identify both the sum of the difference scores and sum of the squared difference scores. So to start, say we have our 15 participants here, right? Our pre-weight, our pre-program weight, and our post-program weight, right? So we have both of our participants here, or both groups here, and note that these are the same people, right? Pre-program and post-program. They're the same people. So we have participant 1, 2, 3, 4, all the way down through 15, right? So it's important to know that these are the same people. So if we're asking the question, is there a change in weight between the pre-program weight and the post-program weight, then what we have to do is we have to pair these people with themselves, right? Pre and post. So we start by calculating the difference score. And what the difference score is simply the post weight minus the pre-weight. So we'll go ahead and do that, and I'm going to use formulas here just to make it a little bit easier. So what I'm doing is I'm going to push equals. That's how we do it in Excel. And so we're going to do the post-program weight minus the pre-program weight. And we'll hit enter. And as you see, the person actually gained 3 pounds over the post versus pre-program. And what we can do is we can highlight this and we can bring it all the way down. So I'm just going to do this to cheat, right? I'm just going to do this quickly, so you guys can get a sense of the idea of how we do this, right? So again, it's post-program minus pre-program. And we have to do that for every single participant, right? So if there's 100 participants, we have to do that 100 times. So now what I'm going to do is I'm going to take these difference scores and I'm going to sum them for this equation here, the sum of the difference scores. So all we're going to do is essentially add all of them up, right? Participant 1 plus participant 2 plus participant 3, so on and so forth, all the way down through participant 15. And the way we do that in Excel is we do our equal sign, and then we do sum, and then an open parentheses, and what we can do is we can take the first one and drag it all the way down, right? And then close parentheses, and that will sum up those scores for us. So we now have our sum of the different scores, which we find is negative 666. Now what we want to do is we want to start figuring out how to sum the squared difference scores. So we now have our sum of the difference scores. Now we need to sum the squared difference scores. So what we do is first let me note, sum of the squared difference scores is not simply squaring negative 666. So I'll do that real quick just to show you what that is, right? So negative 666 times itself is the squared, right? So just to note, that's not what the sum of the squared difference scores are. I'm just putting that here just to show you how different the numbers will be. So to get the sum of the squared difference scores, first we need to square the difference scores. So the way we do that, right, a square is simply the number times itself. So what we'll do here is we'll take the difference score and we'll multiply each difference score for every single participant by itself. Right? So in this case, for participant number 1, it'll be 3 times 3. And we do that for the rest of the sample. And like the sum of the difference scores, the sum of the squared difference scores is again the sum of this column here, the sum of the squared differences. So we do the same thing. We do sum, open parentheses, all the way up, close the parentheses, and there we go. So as you can see, this is about a tenth the size of this one. So again, it's extremely important to know the difference between the sum of the squared difference scores and the sum of the difference scores when they are squared, right? And you'll see those calculations.
So now that we have our sum of the squared difference scores, our sum of the squared differences, our sum of the difference scores and our sum of the squared difference scores, we can start plugging those numbers into our formula. And so here we go. Here's the formula just as a reminder, right? So sigma d is the sum of the difference scores. Sigma d squared is sum of the squared difference scores. And then n, of course, is sample size, and that's the number of pairs, not each score. And so we'll go through these calculations each in a row, and I'll show you how I've solved it. If you can do this a little more condensed, go for it, but I went step by step here, just as an example. So what I've done here is highlighted in color what goes where. Right, so we have our sum of the difference scores at the top, negative 666. We have our sample size, which is 15, and you see that in red, our n. In green, you'll see the sum of the squared difference scores, right? So that's the number in green, and then you'll see the sum of the difference scores squared, and that's in blue. And so in blue, what that number is it's 666 times itself, or 666 squared, right? And that's what the calculation shows there. So it's really important to get those right. It's very easy to switch the blue and the green, so you do not want to switch the blue and the green. You want to make sure that the green is on the left and the blue is on the right. So after we've plugged all these numbers in, so we can plug all these numbers in, and just to go back here, what I'm doing here is I'm going to start from the bottom and I'm going to solve just kind of going up. So I'm going to take that first equation where we have the n times the n minus 1. I'm going to solve that first. So I solve that. We have 210. Everything else is the same. I'm going to take that back. I actually also solved the blue equation as well for 3,556 divided by 15. So in this case, I solved two equations at the same time. So move over here, and so it condenses it just a little bit. The the numerator is still the same, negative 666 divided by 15. Then I'll continue solving each of these equations. So what I've done here is solve the top section here, the 41418 minus
29570.4. I've solved that. And then what I'm going to do is divide that number by 210, so I'm still in the denominator here. Okay, and so we have the square root of 56.1417 that we need to solve. So we can go ahead and solve that. Then we can go and tackle the numerator. We can solve that. And so this is our final calculation. So all of that boils down into this. So it's negative 44.4 divided by 7.511. And what we find here is our t of our observed value is negative 5.91. So now the question is, what does that mean? What do we do with that information? We've gone through this whole big calculation. We calculated d-scores, different scores. We calculated some of the different scores and so on and so forth. What do we do with this now? So after going through this entire process, what we can do is we can plot this on our distribution. So what we're looking for is we're looking for a score that is beyond our critical region, right? And again, our critical region is negative 1.761. And so what we find is that indeed our t, observed t, is beyond that critical region. We have a negative 5.91. And so based on this, what we can do here is we can come to some conclusions about our data, about our sample. And so what we'll do is we can make a decision, and we can go to step 5 here, and we can interpret our results. So again, here's our distribution. We see where our negative 5.91 is. It's outside of the critical region. It's beyond the critical region. And so what we can conclude is that our statistics tell us that our weight after the program is less than our weight from before the program, right? So we actually lost weight. People in this program lost weight. And so we have our null hypothesis here, right? So participants have not lost weight versus our research hypothesis, participants lost weight. And we can effectively reject the null hypothesis, right? We're 95% confident that this result didn't occur simply by chance, right? So again, just to reiterate, there's two potential explanations for this result. One, we either have a bad sample, and our sample is not representative, and we got outside of the critical region one of those 5% of the time just by chance, or it was the result of our program, right? So we have two potential solutions there, two potential results there. And so because our critical region we're fairly conservative, and we're fairly confident, we can say for 95% sure, we're 95% sure that it was the program that created this result. And so the question now is, how do you interpret this in English? So let's talk about that for a second. So how I would interpret this, right? And you can use your own interpretation, but I highlighted the pieces that really need to be placed into a sentence like this. So how I would write this is something to the effect of, a paired sample t-test revealed that participants of a weight loss program lost weight, weighing significantly less post-program compared to pre-program, right? And so the two pieces in blue highlight that that what type of test that we used, and also highlights that it's significantly less, right? And which scores were significantly less. And then in red we have all of our data, right? So we have our data from our mean from our post-program, our standard deviation, our mean and standard deviation from the pre-program weight, and then our t-test, right? So again, the 14 in parentheses next to the t is our degrees of freedom, and then we show our observed t at negative 5.91. And then our p-value is our alpha, right? What we're saying is that our results indicate that we're less than 0.05, which is the alpha level that we identified. So after all of that, we can come to the conclusion that it was the program
we're 95% confident that it was the program that made a difference here. It was the program that helped people lose weight. It wasn't some anomaly in our data. It wasn't just simply by chance that we got the results that we have. So again, thinking about this model, right, this is a very similar 5-step model that we will be doing going forward. The difference here is that each test, when we're in this hypothesis testing area, when we're talking about hypothesis testing, each test does something slightly different, right? So for us, for the paired sample, what the paired sample does, again, just to conclude here, is that the paired sample tests pre and post scores, right? So it pairs people by their pre-score and by their post-score. And so we typically use this, again, for things like weight loss programs where we're measuring things either over time or at a pre and a post period. Specifically, really, to look at the change over time. And so hypothesis testing, we'll continue down this. We'll talk about independent samples, analysis of variance, and chi-squared coming up next. And we have a few more left on inferential statistics, and then we'll be moving up onto bivariate statistics. And that is your daily dose of statistics.